Okay, so we continue with the final talk of the morning session. So we're very happy to have Karen Yeats, who's the Canary Research Chair in Combinatorics in Quantum Field Theory here at the CNO department in Waterloo. And today she's going to talk about the algebraic underpinnings of quantum field theory. Take it away.
All right, thank you very much, Alejandro. Thank you very much to Ian and David for having built so much of the combinatorics that we all do. So I'm going to talk about algebraic underpinnings. Of quantum field theory. Okay, and the connection with the topic of the conference is some work of David Jackson along with Achim Kempf and Alejandro Morales on, well, I'll tell you what it's on in a moment. So I'm going to start by telling you a little bit about what their work in this area was. Then I'm going to tell you a little bit about some of my own work in this area. And then I'm going to conclude by a somewhat speculative program for where we could go from there in terms of this approach. So let me start my first section by saying that there are a lot of formal power series in quantum field theory. And in perturbative quantum field theory in particular. And so what do I mean by this? Well, if you sit down and you open up a quantum field theory textbook, and unfortunately you will find it's not written for an average combinatorics reader, but anyway, you open it up anyway, and you start reading it, and you will see if they, especially if you take an older, more classic quantum field theory textbook that has some focus on the perturbative approach, then you'll find that they write down this thing that they call the path integral. And from out of that, they get some sort of series of Feynman diagrams. And they do stuff with them, like predict things that you could calculate at CERN, like do real physics where you can compute stuff. All right. And so what is the overall idea here makes a certain amount of sense. Because what is the path integral? The idea is sound. The idea is saying, well, I guess you can think of it a couple of ways. You can think of it in your sort of overall sketch view of quantum things in general that you want to sum over all of the possibilities. But of course, they're not discrete possibilities because you have some, you think of your fields are some functions, you have some function space of possibilities. So you need to integrate over all of these possibilities. Another way you can think of it is you can think of it as going back to if you've done some more classical physics where you have some action and you want to write an appropriate integral over the action to minimize something or to make your physics work out. Okay, and I'm going to write down one way to write down the path integral right now. I'm going to use exactly the notation out of the work that David, Achim, and Alejandro did, just so that if you're going back and looking at their paper, you don't have to do too much translation. All right, so I've got some path integral, and I'm going to write it like this. What am I going to do? Well, I'm integrating over the exponentiation of the action. Well, I'm going to change color in a second, and I'll mark out what some of these key pieces are. And then there's some other part, which I'm going to have some D4. Oh, I said I was going to write it exactly like that. Okay, I turned into a physicist briefly. Sorry about that. Well, it's not a very big difference. And overall, no, I'm halfway a physicist. Okay, I'm going to go all the way to physicist. I don't know if you've noticed, but physicists like to put the D right by the integral sign. It's kind of nice. Okay, there we go. Now let me just get another color and point out what some of these bits and pieces are. Because this S here, what is this S? This is your action. And you want to think of it as something like an integral of your Lagrangian density. And maybe as a simple example of something that will work for us, you could think of your Lagrangian density as being something like this. So you've got, say, something like this. I guess I want a half here. So that would be a Lagrangian density for a massless 5-4 theory, but you don't need to worry about that. So you can completely ignore this part if you don't like it. because we'll get back to how you should think of this in a combinatorial way in a moment. What are some of the other pieces? What else is up in this exponential? So this is a source or a source term. And this guy is your field. And then here's where you get your trouble. What are these guys? Somehow I'm integrating over some space of all fields, but that's just simply not analytically well enough behaved for this to actually mean anything at all in a mathematical sense. But still, it's quite insightful. And physicists have spent many decades getting a lot of really useful and interesting stuff out of this. But we can take another approach to try to think about this, right? Rather than, because this is a story we all know, right? We have some sort of thing, and sometimes it makes sense analytically. It makes sense analytically if I'm in a zero-dimensional case, but it doesn't work all the time. So maybe the correct approach is not to think of this as an analytic object, or at least not to think of it as an analytic object first, but to think of it in terms of formal power series. So and even better, they're not just any old formal power series. In fact, they're generating series. And so, for example, I've been working in what's known as, I wrote down a Lagrangian for a massless phi 4 theory. Okay, what the heck is that? How can I see this as actually being a generating series for something? Well, I can think of this, it's some sort of sum over graphs. And here very briefly, if you want to actually do this calculation, if you've seen the sort of approach to enumerating maps via these kind of path integral type formulations, then you know exactly what I'm going to say. In fact, this is sort of the original motivation for that approach. So what do you want to do here? Well, let's say I want to have a source and a sink, so two J's. Well, if I got two J's, I got two of these guys. And here, since I've got some derivatives here, I'm going to be pairing things up. And so what am I doing? Well, I got a source and a sink and stuff in the middle, and I don't know what's in the middle. And I'm going to pair that up in all possible ways. Well, it could just go straight through. That's one way it could happen. And notice I'm going to have to, because of the 4 here, whenever I make a vertex, it's got to be a vertex of degree 4. So here's something else that could happen. That's a perfectly good thing that could happen. This has a factor of a half, which we'll get back to in a second. What else could happen? Well, it could go straight through, and another one could do something like that. Okay, so there's two connected components there. Could also do something like this. It's a perfectly sensible thing for it to do. What else could it do? Well, I mean, those are all kind of annoying. What about this one? I like that one better, etc. I'm not going to draw anymore. I am going to finish, though, putting in some symmetry factors. So the point is, this guy here is a generating series for some kind of graphs. And if you don't already know any of this story, you don't have to worry about exactly what kind of graphs. But for this particular example, I have 2 external edges, and everything inside is 4 valent vertices. And that's, I'm just going over all of those graphs. Okay, so that's nice. That brings us into a world that we understand. So now, there are a couple of details that matter. So first of all, this does not look the same as this, right? Like there's like an integral in there and stuff like that. And so if I'm working over, if I can get rid of, if I don't have this integral here, this 4 incidentally is the dimension of space-time. And I chose 4 because I kind of like this world that we live in, and it's got 4 dimensions, right? It's got these 3 dimensions plus time. So that's why it's 4. But now, if this was actually 0, there wouldn't be an integral here. There's just a point here. And then this is also nice and well defined, and you can really do this integral. That's the story of 0-dimensional field theory. And then you really are just counting. But if you actually want to do quantum field theory, then you need that integral there over however many dimensions of space, however many dimensions your space-time has. And so when I write down this series, then I don't really just mean the graph, because each graph is going to come weighted by its Feynman integral. But that still fits into a nice generating series kind of context still. It's just these now have some sort of weight. It's coming from something that, okay, it is somewhat analytic still, although I'll get back to an example where I can actually take out all of that as well. Okay, anyway, we got these guys. Now, I do want to make a note. If you actually did the calculation, pulling these out of the path integral, you would in fact find these coefficients coming out. But as you're staring at them, and in fact, as I gave that very brief description of how you would pull them out, you might perhaps see what's going on. This is secret labeled counting. Secret labeled counting. And now, again, if you look in your quantum field theory textbook, they'll write something like this, that the graph comes with a factor of 1 over the size of the automorphism group of the graph. Well, what is that? Well, that's just, if I took a labeled graph instead, then it's 1 over your good old n factorial. Just labeled counting. Exactly the way you would expect. Now, wait, you're saying, wait a second, what the heck are we labeling? The answer is we're labeling the half edges, but these external guys are being considered to be fixed. So here, where's half symmetry coming from? It's coming from the fact that you can take this little blob and go and flip it around. Okay, and similarly, this one you can flip either one, or you can swap the 2 of them. You can flip these. And here, clearly, I have a 3 factorial going on with these internal guys. But I'm not allowed to flip the whole thing around because I want to think of the external guys as being pinned. And that actually comes from the original physics motivation for the problem. Why are your external edges in your diagrams pinned? Well, what are your external edges? In a scattering experiment, like you're at CERN, you've got beams of particles coming in, some stuff happens inside, and you have no idea. But then you have detectors outside that are detecting the things coming out. So what are the external edges? They're the particles coming in, the beams that you made, so you know exactly what they are. And then the stuff that came out, which is the stuff that your detectors found. So you know exactly what they are. So they're specific guys that you have. And so they're considered fixed, like pinned from a sort of counting perspective. Okay, so this is secret label counting. All right. Now, the physicists knew that this was secret label counting. So if I have labeled counting, then I know how to get rid of this annoying disconnected guy. That's easy. I've got the X log rule to do that. So I can take the logarithm. And in fact, I want to put an I, and I think I want to put a negative sign. Do I want to put a negative sign? I do want to put a negative sign. And I'm going to call this W. And so this guy would now give me the sum over connected Feynman graphs. And so this is, in a physics language, it would be a generating functional for the connected diagrams. And it's exactly what it seems to be, a generating function in our sense as well. And this is classical. Physicists knew this. They didn't exactly think of it as secret label counting, but they knew that it was implicitly, and they knew this result. Okay. But there are some more series operations here. It looks like I'm still on the screen, okay, so I'm going to keep going a little further. So there are more formal power series. Well, let's not say that yet. Let's just say there are more series operations for the moment, and we'll get back to formal power series in a sec. And I'm going to go in two directions. I'm going to go backwards and I'm going to go forwards. So what do I mean by that? And if you think that I started with the path integral and then I went to the connected guys, well, let's not do that. Let's go back the other way. And I can go back the other way by noticing that this, if I sort of ignore the fact that I don't even know what the heck a bunch of this stuff is, then this kind of looks like a Fourier transform. The Fourier transform. And so let's notice that. And let's go backwards using a Fourier transform. Okay, so I can say, okay, look, this looks like a Fourier transform of this exponentiated action. Okay. What about the other direction? Well, by going to connected, I kind of got rid of this guy, but I don't like this guy either. And the reason I don't like this guy is because it has a bridge. Okay, now if anyone's wearing a graph theory hat, remember, these are external edges. You should think of them as just halves. The other half is not there, so they don't count as bridges. Don't count these guys, but that guy really is an honest to goodness bridge. And I don't like that. I don't want that bridge there. So the other thing, and physicists knew, to go forwards is to go from this Wj to the bridgeless, or physicists would say one particle irreducible, so 1 pi. By, how do they do it? They use a Legendre transform. Okay. But I was saying that with a physicist hat on. And now if you come back to this with a mathematician's hat on, you say that this actually makes no sense, because the Legendre transform, I mean, that's something in analysis, right? You're like, I don't remember what the heck that is. Okay, that's fine. Go look it up. But it's a thing, and there's some analytic hypotheses in order to be able to apply it. And you know what? They're not satisfied. So what the heck is going on here? Well, we have a program. What the heck is going on here is you should not think of these two things as analytic transforms. You should think of them as formal power series operations. And then you just need to check then that the correct hypotheses for the formal power series operations are satisfied, and they are. And that's exactly the way this should work. And that's what Achim and David and Alejandro showed us, right? So Jackson, Kemp, Morales said these two directions, these are formal power series operations. And then everything is happy, because then then it actually works rigorously, and you can do exactly what you want to do. And yeah, you're happy. Okay. Yeah, furthermore, they're not just formal power series operations, but all the steps are really combinatorial. So which means that they have a meaning or an interpretation. And let me just show you for the Legendre transform. What is the Legendre transform? This is about treifying or detreifying. I think David is probably really mad at how I'm completely destroying the English language here. Okay, so what is the idea? You have a 1 pi thing in here, and then if you make a tree out of 1 pi, guys, remember 1 pi means bridgeless. Oh, can you see this behind the podium? You can see, okay. So if I make a nice tree of 1 pi, guys, Well, in fact, I can build an arbitrary graph out of a tree of 1pi, guys. And likewise, if I have a graph, I can form the tree. I can take the bridge edges, and they define me some connected components, which are bridgeless, and they're joined together in a tree form. So this is what Legendre is. And they prove that for us. So I think this is very nice. This says that the sort of central story that we try to say in perturbative quantum field theory is something that first exists on a purely formal and combinatorial level. And okay, then if things are nice and you can do some analysis as well, that's bonus, but it works here and is rigorous. Now, let me tell you another example where this kind of thing comes up that's coming from my own work in this area. Haha, the blue doesn't erase right. It's maybe pre-COVID. Maybe it's a pre-COVID marker. I don't know if any of you had that problem when you got back to your office for the first time after COVID and all your markers were a little bit off. So for 2, I want to talk about Dyson-Schwinger equations. And I want to claim to you that the story is actually rather similar here. Now, at some level, it's just something that lives inside the story that David and Akim and Alejandro were thinking about. But it's sufficiently nice that something a little bit special happens. So what's the point here? Well, if I'm doing enumeration by formal power series, like enumeration by generating series, one of the big tools that I want to use is I want to use the fact that if I have some combinatorial decomposition, then I get some functional equation for the generating series, and then I do stuff with it, right? Like that's the central method that you use. Well, surprise, surprise, that's also something the physicists knew how to do and that we can reinterpret in this combinatorial language and get a lot of leverage out of. So, and these are the Dyson-Schwinger equations. So what are Dyson-Schwinger equations? They're the quantum analogs of the equation of motion. Okay, but what the heck does that mean? That's just some sort of crap that you like to write when you're giving a talk, right? That's what you're thinking. You're thinking in your head, that's just some sort of blah that she should put in her grant proposals and not on the board. Well, what I'm just trying to show you that there's something important about them. But they're also these sort of structural functional equations for, well, exactly these guys that we were talking about. I don't think I gave this one a name. I think they call it gamma. So let's call it gamma. Give functional equation for these gamma guys. And they're sort of, they have with combinatorial structure, let's say. Okay, let's continue this example. So if I'm in phi 4 again, maybe I'm still interested in this guy. Well, what could it be? It could just go straight through. We already said that. Oh, but this is now 1pi. So I'm just doing the 1pi guy. What else could happen? Well, there could be some first vertex. And then some stuff could happen here. And then some more stuff could happen. And that's all that can happen, really. Okay. But what's the stuff? Well, this, I could insert one copy of it in here. Like if I have some graph, one of those 1pi graphs, I could insert it in here. But I could also insert 2 of them in a chain, or 3 or 4, or you know what the heck this is. This is a geometric series in this guy. So I'm going to use a different color, and possibly I have a different color that's not quite as dead as this blue. So let's try this one. I'm going to write a red here. And now I better tell you what that means. Where, and here's where you're going to be really annoyed, because this is what a physicist would write. Hey, it's an inverse propagator. What do I really mean? I really mean geometric series, i.e. geometric series in what you can insert there. And this guy would be a 1 pi 4-point guy, and you could similarly expand it. I mean, it would start with the 4-valent vertex, and then more stuff would happen, and I'm not going to write it all out. The point is, this is just a recipe for how you can build all the 1 pi graphs out of inserting graphs into each other. But now if I say again that, well, I write this down, this notation with the blob, anytime I write a blob, it's really just a generating function for the graphs you can make with whatever you're allowed to have in that blob, right? So this is just some system of equations for some generating functions. And this is the Dyson-Schwinger equation, the diagrammatic form of the Dyson-Schwinger equation. Okay, so that's nice. That's saying, look, it's the same story. I'm just looking at it in a slightly different part of it, slightly different direction. Okay. If I took this one for just a moment, I'm going to write it down so it looks a little more analytic for a moment, just to give you a hint of what's going on. So if I'm now going to call this, I'm going to call it GXL. This is some particular value, so I might as well normalize it to 1. And then what's going on here? Well, inside, there's something like a GX, well, let's say K1, GX, K2, GX, K3. That's the 3 guys here. The L has to do with the momentum flowing through, and so there's different momentum flowing through each of these. Hey, that goes back to what we were talking about just a moment ago with flow polytopes. Did you know that that's actually kind of what the physicists are doing? Because when you write the Feynman integral in momentum space, you are integrating over all the possible momentum flows through the graph. Except I like my momentum flows to be R4 valued, or maybe Minkowski 4 valued, depending on how you want to think about it, which is a little bit of a weird choice of space, but hey, it's the same thing. It's just flows. But anyway, these are these guys without defining exactly what all my terms are going to mean. This is the G for the propagator. There also should be a G for the vertex. Oh, I'm not going to call this X, sorry. I'm going to call this alpha because X is something else on the previous, on what used to be under here, it was something else. And then this is actually got to be a function of all of these. Okay, and now what's still going on? There's still sort of a residual piece of the Feynman integral that just comes from these outer guys, just comes from the sort of explicit cycles you would see if you contracted all these pieces. And so that's some integral, there's some d4k1, d4k2. Under here, there's going to be something like a k1 squared, k2 squared, k3 squared. Hey, wait, you said they were R4 valued. How the heck do you square them? They're just norm squared. That's just how the physicists write it. And then I need to renormalize, which I'm not going to tell you about today because that's a different story. But the point is, you just write something like this, and you have these G's. They're taking the place. They are the generating series, really, but they actually have the Feynman integrals in them, and that's why there's some analytic stuff. And you write something down, and it looks a little nasty, but if you, again, think of all these as formal power series, it's not too crazy. Okay, well, I'm not going to solve any of these for you. I am just going to check the time, because one of the consequences of COVID, for me anyway, is that I lost my ability to time my talks exactly just from my head. So now I have to check. Okay. Again, if we're in the zero-dimensional case, which is the graph counting or map counting case, dimensional. Oh, Sorry, that's a problem. You start talking in the middle of writing a word and then it's not right anymore. In the zero-dimensional case, there's no integral. And then it really is just these diagrams. In general, well, I want to get on to the last thing I want to say. So I'm not going to tell you the details. Some of you, if you've heard me talk blah, blah, blah about Dyson-Schwinger equations and chord diagram expansions and things like this before, you know that I actually know a different way of expanding nice examples of this, which is in a certain sense purely combinatorial. So here it's sort of semi-combinatorial, right? It's a sum over graphs, but each graph is contributing a Feynman integral, which is a kind of complicated thing. And so I know how to rewrite nice ones of these. So in general, it's not quite right. In higher dimension, let's say, in dimension greater than 0, if I'm only looking at propagator insertion, so that's just one, it's just something coming in and going out, there's not extra stuff. And so all propagator insertions, I can rewrite this as a sum over, well, there's two ways to do it. If you've heard me talk about it before, I probably talked about it in terms of connected chord diagrams. But the recent news is I can also think of this in terms of tubing trees. And I hope there'll be a paper out in a few months on that. Anyway, the point is, so continuing this paragraph, with each only contributing a polynomial, and actually a pretty nice, easy to control polynomial, as opposed to contributing an integral that's actually analytically very hard. If you're the kind of person like I am that's used to leaving the analysis to someone else, it's kind of easy to think, well, integral, who cares? Just give that to somebody else or give it to a computer. But actually the convergence properties of these are really poor. So they're hard to integrate even numerically. And there we go. I can redo it. So, well, I'm slightly sweeping under the rug exactly what the coefficients here are. But basically there's one integral. You have to sort of one universal integral for each primitive diagram. It's a little bit of a story, and it's not today's story. The point is, it's still about series expansions, and they're even more combinatorial than they used to be. Because now more of the weight is just about counting various with various parameters on chord diagrams or tubings of trees. So personally, I think that's really nice. Okay. What next? What was the title? It was the whole overall title was Algebraic Underpinnings of QFT. And don't worry, this section won't have a subsection that also has that title, because that would be really annoying. But now let's think. So I started by telling you a little bit about some work of Jackson, Kempf, Morales, and they have a recent paper, and I want to tell you what the title of their recent paper is for those of you who haven't been following this. It's called Towards a More Algebraic Footing for Quantum Field Theory. And I think that that is very much on point and exactly what I'm also aiming for here. So what did they tell us in what they wrote? They told us that perturbative expansions are formal power series. Okay, and they're not the only people to have said that, but they build up some important parts of the theory of how this is going to work. In fact, they're more than formal power series, they're generating series. And again, they're not the only people who made this observation. They also observe, and I think they're completely on point with this observation, that these combinatorial proofs are better, right? In what sense? In two senses. And they're better in the sense that they're more powerful because they don't rely on these analytic hypotheses that often get swept under the rug by the physicists anyway, because they're not even true in the case that they want to apply it. So don't require these analytic hypotheses types, which are false in the cases of interest. And they're also better, and I think we all understand this in this room, they're better because they provide insight, right? And this is similar to the way to thinking in terms of a physical proof, right? So like a physical proof, they provide insight. Okay, and what do I mean by that? So if any of you guys work in areas that come in substantial contact with mathematical physicists, you probably have a bit of a vision of this sort of mythical physics intuition that somehow physicists sometimes seem to know the result before they should at some level, right? That's because they have a strong physical intuition for what's going on in a situation. But that's really the same thing that we're getting from a combinatorial proof, because now we have an interpretation for what all the bits and pieces are. And so you can sort of see how these bits and pieces can move and fit together. So that same kind of insight is why the physicists seem to have this magic intuition. And that's how we can have it too, right? So that's why these kind of combinatorial proofs are better. But now, I think really there's a bigger program here. Okay, and I'm going to make a little line from less speculative to more speculative. Less speculative. Maybe that's not quite true, because some at the top I'm going to write down some things that are theorems, and those maybe aren't speculative at all. Oh yeah, I said known in my page. Let's say known at the top to speculative at the bottom. That's a better. That's the scale here. This is from known to speculative. All right. I don't want to mess them up, so I'm going to make sure I actually say all the things I want to say. Yeah. Okay. So there's this stuff that was already here. Let's give this a name. Yeah. So star comes first. That's definitely here. That's known. That's the Jackson temporalis, etc. story. Well, what else can you also do? If you just go look up, algebraic and combinatorial things in quantum field theory, you might not get that story first. You might get another story that I'm pretty closely associated with, which is the story of UV divergences by renormalization Hopf algebras. Let's just say combinatorial Hopf algebras, because they are examples of combinatorial Hopf algebras. And notice that this connects to here, because although usually you will see this presented graph by graph, but it's also true that it's well behaved at the level of these generating functionals, or Green's functions, as I would usually call them, because I like to think of them as solutions to the Dyson-Schwinger equations. So this is also, so this works. It works either graph by graph or on these generating functionals. So it's part of this story too. This is something that you can see as you can take your formal power series, that's this sum over graphs. You can toss the graphs in. So now instead of just having a sum over the weight of the graph, let's have a sum over the graph times the weight of the graph. So this is now something that has coefficients in some Hopf algebra of Feynman graphs. And now I can think of the renormalization map as something that acts on that series with coefficients in this Hopf algebra. Okay, so that's nice. That's something that makes sense. Well, what else can you do? If you're out talking to a physicist, they might be really unhappy because they say, oh, this is just perturbative. You can't see the non-perturbative stuff. But you can, because you can go on to work with trans series to get, say, instantons and other non-perturbative effects. But that still lives inside this story. Because what is a trans series? A trans series is something where instead of just having monomials x to the n, you also have as sort of base pieces that you're allowed to have use as your things that you're making sums over. You also have things like e to the minus 1 over x and log x or log 1 over x, whichever one I'm supposed to have. I think I'm in inverse variables, so I think I'm on log 1 over x. So you're allowed to build a larger class of series expansions, just with more pieces. And I think trans series are actually something that more of us should know about, because so trans series are something that was simultaneously found by analysts and logicians. That's a really good sign that there's something really right about them, if they're the right object in two such different parts of mathematics. And the reason is because they're closed under a bunch more operations that you would like to have, which formal power series aren't closed under. Okay, now this is certainly something that makes sense at a series level, and it tells you stuff, and there's results of Misha Berinsky and Gerald Dunn, for instance, where they do an instanton analysis of some Dyson-Schwinger equations of the type that I was telling you about earlier, and they can get some really interesting results. It's not completely clear that it's combinatorial in the sense that there are combinatorial interpretations for the coefficients of these series in these generalized series. I would certainly like to see that it is, but it's not clear yet. So it's not totally clear how combinatorial it is. It's certainly nice series work. Okay, what else is there that's in this picture? So notice I said UV divergences, and you're like, what the heck is UV divergences? UV is what I put the sunscreen on for, right? Like, so, well, why do you put the sunscreen on? Because the ultraviolet rays are the high energy rays. That's why they burn your skin and give you cancer, right? So these are divergences that are coming from taking that integral at high energy levels. You can also have divergences that are coming from other places, from low energy levels, and those are called, surprise, surprise, infrared divergences. And infrared divergences, they relate to things like cuts in graphs, and they relate to questions about when particles are on shell, which I'm not going to go into. And this should also be a combinatorial story. It's a little bit less clear. I have a little bit of work with Dirk Kreimer looking at some of this from a Hopf algebraic perspective. It's a lot, the details are a lot hazier to me, but I think there is something definitely there. And ultimately, at the bottom of speculative, we started with the path integral, right? And remember it said, oh no, it said it right here. Oh no, I can still see it because the blue didn't erase properly. Ultimately, I think this is a picture, a story for giving new foundations to the path integral. And I'm not saying I know how to do that, but I think this is the right way to think of it. And there are many people out there thinking about giving a rigorous mathematical characterization of the path integral, but they're mostly taking an analytic perspective. And I think that's a mistake. I think we want to take this kind of formal series perspective. And I hope then that ultimately we can refound the path integral. With formal power series and combinatorics. And there's many other details. This is substantially what my own research program is about, but it's also, I think, it closely relates to this very interesting recent work of one of our honorees. And I'm going to stop there. Thank you.
Wonderful talk. Any questions for Karen? So I have a question. When you mentioned for the Dyson-Schwinger equation, the tubings and the connected, are those, can you use bijections to go from one to the other, or?
Yeah. So that's one of the things that'll be in the new paper is a nice bijection between rooted connected chord diagrams and tubings of certain rooted trees. The tubing picture, it seems to generalize more naturally, and so I think that's been the recent insight that was just over the course of the last few months.
The questions for Karen. So let's thank again Karen for the wonderful talk.